So today what we're going to start talking about are imaginary numbers. So imaginary numbers were invented to define the square root of negative numbers. So as you've known up until this point, if you have the square root of a negative number, you couldn't figure it out. Now we're going to be able to figure out there is an answer for it now. So the imaginary unit I is defined as the square root of negative 1. I is the square root of negative 1. So imaginary numbers can be written in the form a plus or minus bi. So a just represents some kind of real number. It could be a fraction. It could be an integer value. It could be a radical like the square root of 2. Any kind of real number. That is what a is always going to be. And then b and the I create the imaginary unit. So you've got the real number and then you've got imaginary unit. Put them together, you got your imaginary numbers. One thing to note, the square root of negative 1, which again, the square root of negative 1 is your I. But if I were to take that and square it, remember that means it's the square root of negative 1 times the square root of negative 1. What does that end up equaling? Negative 1. Remember that square root sign and squaring, they end up canceling each other out. So the square root of negative 1 squared is just going to give you a negative 1 again. So we'll get into that in a little bit. Let's first practice figuring out our imaginary numbers. So we're going to start off with the square root of negative 25. So for this one, I would separate it into the square root of negative 1, so that takes that negative out of there. And then 25 is a perfect square, so I'm going to leave that as the square root of 25. So the square root of 25 is 5, and then the square root of negative 1 makes that become I. So 5i is our answer for that one. All right, second one. Again, I'm going to take out my square root of negative 1. Which means I'm left with just the square root of 121. So what is the square root of 121? 11. And again, that square root of negative 1 makes it I, so it's going to be 11i. Third one, again, I take out my negative 1. So I'm left with the square root of 7. Is 7 a perfect square? No. Is there a perfect square that goes into 7? So this one's just going to turn into I radical 7. So that negative always comes out and turns into an I. So fourth one, what would the square root of negative 16 turn into? Yeah, which would be 4i. You don't always have to show that step of separating them. You can skip that step. But then we would do it still times the 3. That rule still applies. That 3 was out there in front, so it's going to get multiplied by whatever comes out of the radical sign. So it's going to be 3 times the 4i, so 12i. So for the next one, negative 8, what's our perfect square from negative 8? 4 and 2. Square root of 4 is 2. Because it's negative, it's going to be 2i. And then radical 2. Again, you can write that middle step if you need to. 6, what's our perfect square that comes out of 75? 25, and it turns into a. So times the 2 would give me a 10i because it was negative. So I get that I there because it's negative. And then the square root of 3. All right, so let's play around with some operations. We'll add and subtract them. Adding and subtracting i's is just like adding and subtracting x's. If they have the same exponents, you can actually add them together. So let's take a look at this first one. Square root of negative 81, what would that turn into? Negative 9i, because it's got that negative out in front, so that's why it's a negative 9. And then the square root of negative 121, 11i. So again, it just follows those rules, just like we would use for our x's. Negative 9i plus 11i would become 2i. All right, 8. Square root of negative 9 would turn into what? 3i, and then times the 2 makes it a 6i. And then the square root of negative 49, 7i, times the 5 makes it a 35i. So now we can subtract 6i minus 35i, negative 29i. All right. So square root of negative 48. 16. So then the square root of 16 is, and it gets an I along with it because it's got that negative underneath the radical sign. So that's where the I comes from. So 4i radical 3. Perfect square for 12. 4, yeah, and the square root of 4 is, so we got 2i radical 3. So now 4i radical 3 minus 2i radical 3, 2i radical 3. All right, 10, perfect square out of 18. 9, square root of 9 is 3, but times that other 3 gives me a 9 again, so 9i and then radical 2. Always put the I in front because you don't want to make the I look like it's under the radical sign. Okay. And then our largest perfect out of 72, 36. This becomes 6i radical 2. A lot of people still want to tell me 9. 72 is always 36 and 2. So 9i plus 6i gives us 15i radical 2. So 11, is there a perfect square that goes into 10? No. But because it's a negative 10 under there, I do have to take that negative sign out and make it 5i radical positive 10. You do always need to take care of the I if it's there. Is there a perfect square that goes into 52? Yes. Yes, there is. Or, yes. So that becomes 2i and then radical 13. And then can I actually subtract those? No, because I have a radical 10 and I have a radical 13, so no. That's going to be my final answer there. So number 12 there, perfect square out of 27. 9. So that gives us 12i, because square root of 9 is 3 times that 4. Makes it 12i. Perfect square out of the 50. 25, so we get 5i radical 2. Can I actually add those? No. So I got a radical 3, and I got a radical 2. So the powers of I are repetitive. I think I spelled that wrong. I don't care. I think I spelled it wrong. That's why I teach math. So the powers of I are repetitive. They follow a pattern, and they just constantly are going through that pattern. So all powers of I can be expressed as one of 4 values. They follow a pattern of 4. So when you're simplifying them, which you will have to do with your exponents, as you do need to end up simplifying it down, it's always going to be one of 4 things. So as we can recall, I is the square root of negative 1. And the square root of negative 1 squared is simply negative 1. That's what we went over last time. So now let's figure out I to the third. So I to the third is the same as the square root of negative 1 to the third. Because again, I is the square root of negative 1. So if I rewrite that, that's the square root of negative 1 times the square root of negative 1 times the square root of negative 1. But as we just figured out, if I just multiply two of them together, what does that turn into? Negative 1, right? Square root of negative 1 squared is negative 1. Which is just negative square root of 1, which would be negative I. Because again, I is the square root of negative 1. So if I'm multiplying three of them, two of them when multiplied turns into that negative 1. You still got that third one. So it's equivalent to negative I. I to the fourth is the square root of negative 1 to the fourth power, which means I am multiplying negative square root of negative 1 times the square root of negative 1 times the square root of negative 1 times the square root of negative 1, multiplying it 4 times. As I multiply left to right, those first two, when I multiply them, they turn into what? Negative 1. These last two, when I multiply them, turn into negative 1. So negative 1 times negative 1 is positive 1. So I to the fourth simplifies down to be 1. So I to the first, here's a little chart here. I to the first is the square root of negative 1. We would leave that one as simply I. I squared simplifies to be negative 1, because when you multiply the two radicals, I to the third is negative I. And I to the fourth, as we just saw, simplifies to 1. And then it just repeats that pattern. Just keeps on going. So I to the fifth is actually the same as I to the first. It just kind of goes back to the top and repeats. I to the sixth is the same as I squared. I to the seventh is the same as I to the third. And I to the eighth is the same as I to the fourth. So I used to do this little table, but I actually found a little clock thing works best. Draw yourself a little clock there. That's I to the first. This one is I squared, which is negative 1. This one's I to the third, which is negative I. And that's I to the fourth, which is 1. So again, it goes through this pattern always, always, always. So my I to the fifth means that it goes through all the way to the fourth power, and then it goes again one more, and that's why it ends up being the same as I to the first. And then I to the sixth, that goes around the circle one whole time, and then you got two more left still to get you to the I to the sixth, so it ends up being the same as I squared. The same thing with the 7th, 8th, 9th, 10th. So like for example, I to the 12th means it's going all the way around 4, 8, 12, ends back up at the top again. I to the 15th would go 4, 8, 12, and then it would stop at 15. So when we're simplifying the powers of I, you want to divide the exponent by a 4 because it follows the pattern of 4. And what that number ends up telling you is it tells you how many times it goes around the circle and how much further it has left to go. So for example, if I am simplifying I to the 11th, use your calculator. 11 divided by 4, what do we get? 2.75. So what that means is in the little pattern up here, it goes around 1 whole time, 2 whole times, and then you got to go 0.7. So you got to go 3/4 of the way. So quarter, half, 3/4. So this is going to equal negative I. So it tells you how many full times around the circle, which you don't always have to do the full times around the circle. But you got to figure out how much is left. Is it a quarter, a half, 3/4, or does it go to 1 whole? Let's take a look at our examples. I'm going to draw my little clock up there to help me as I'm doing this. Promise the clock's going to be helpful. So 25, divide that by 4, what do we get? 6.25. So again, that means it goes around the clock 6 whole times, and then it's got to go 1/4 of the way, which means it stops here, so that means this simplifies down to be just I. So I to the 25th simplifies to be I to the 1st. Second one, I to the 16th minus I to the 28th. First, we got to simplify them, and then we can actually combine. So 16 divided by 4, what do we get? 4. Was there any decimal? So that means it stops up at the top. It's 1, yes. So when you divide, if it's a whole number, that means it's just 1. It goes around full, complete times, and it stops up top. 28 divided by 4? 7. So that means that also stops at the top. So we got 1 minus 1 gives us a 0. So simplify down to give us 0. Here we're taking us back. Do you remember what to do with these 2 exponents? Multiply, power to a power. You got to multiply, so that's I to the 18th there. Now let's divide. 18 divided by 4. What do we get? 4.5. So it goes around 4 whole times, and then it's got to go a half. So that means it's going to be the same as negative 1. Mm-hmm. Just be careful though, because then at that point you had a negative I, it kind of changes things around. You would have had an extra negative in there. All right, 4, let's multiply first. So 5 times 6 gives me 30. This is the one where we add our exponents, so 5 plus 11 gives us 16. So we got I to the 16th. So again, let's divide that exponent by 4. What do we get? 4, so that means it ends up top, so that means I to the 16th simplifies to a 1. 30 stays as 30, but instead of being times I to the 16th, it's now times a 1. So we get 30 as our answer for that one. All right, so 5th one. First we got power to a power, so we got to multiply those ones. So that's I to the 10th times I to the 7th. So that becomes I to the 17th. So 17 divided by 4, 4.2. So it goes around 4 whole times, and then 1/4, so it ends at I. So that simplifies down to I. Pretty much with your I's, you should never have an exponent higher than 4. You always got to simplify them. Yeah. With square roots that have negative radicands, you need to first take care of the negative by making it an I, and then you follow all of your other rules. So for 6, square root of negative 16, that would turn into 4I. Square root of negative 9 turns into 3I, so you have to take care of that first. Now I can actually multiply. 12i squared. Yep, and then I squared turns into, based on our little circle, turns into -1. So we get -12. Taking a look at number 7, negative comes out as an I, so we got I radical 7 times I radical 2. Take care of your i's first. So now out front, I times I squared, and then we get radical 14. But then I squared simplifies to -1, so we would get negative square root of 14, or -1 square root of 14. 8, again, we got to take out the I from that first radical. So it becomes -2i radical 3. Second one didn't have a negative, so that stays as 4 radical 5. So now when we multiply -2i times 4, will give us a -8i. And then under the radical sign, 3 times 5 gives me a 15. -8i radical 15. Nine, we have a distributive property, but again, we got to first take care of our negative right there. That becomes 2 radical 6 plus I radical 30. Because there's no perfect square that goes into 30, so I can't simplify that anymore. Now we can distribute 2 radical 18 plus I radical 30 I wrote 90 and I said 30. Yeah, I wrote it right at least. So then the square root that comes out of 18, or perfect square that comes out, that makes that 6 radical 2. Perfect square that comes out of 90 would be 9 again, so that becomes 3i radical 10. Then our radicands are different, so we can't add them. So then our last one there, again, what's the perfect square that goes into 80? 16. So we got 4i radical 5. Bottom, all you can take out is an I, so I radical 5 for your denominator. So now what can we cancel? The i's can cancel, and the radical 5s. So our answer for that one is 4. So in our perfect square out of 24, 4. So 20i radical 6 over -2i radical 3 Okay, so i's will cancel. I'm going to cross those out. 20 divided by -2 gives us -10. And then under the radical, 6 divided by 3 gives us radical 2. So we almost had to rationalize that one, but luckily 6 was divisible by 3. So 6 divided by 3 gives us our radical 2.